So, good evening, everyone. It's a real pleasure to welcome you this evening to the inaugural professorial lecture of Nick Pears. Nick's been in the department since 1998, which makes it interesting because not only does he have a professorial lecture this year, he's also having a long service award ceremony later in the year as well. I'm not quite sure what's been going on, but I can't work out. I think I've been following Nick around inadvertently over the entirety of my life. Nick did his undergraduate PhD in Durham, where I grew up. We were in Durham at the same time, but I was at school. Then he moved to Oxford, where I did my PhD, to work in robotics, working in particular in mobile robotics. I then moved on to Cambridge, so quite notable in working in both Oxford and Cambridge, where I also moved in the 90s, but not to study at Cambridge. I didn't actually make that move. I was actually working in a company. And then at which point our paths seemed to have parted ways, and Nick went off to Glasgow for another postdoc before finally coming to New York as a lecturer, where he's sort of flourished over the years, working in the Advanced Architectures group and also in Vision, Vision area, and now in the Vision Graphics and Learning group as well. And I was then for a bit of a shoe-in and finally arriving at York about 10 years after you. So I think I'll let you have a bit of peace somewhere along the way.
Do you want to know where I'm going next?
No, I think we'll let fate decide that. Okay. So it's a real pleasure to have Nick give this lecture. I'm really looking forward to hearing about your research. I won't steal any of his thunder, but Nick's been a great member of the department, contributing throughout to the rich life of the research of the department, as we'll hear about tonight, but also the education and the students' lives that he's been able to teach whilst here. So it's really great to have you here, and I'm really pleased that you're a professor and able to tell us all about what you do. So
thanks, Paul, for the kind introduction, and welcome everybody, and welcome to everybody online as well. My talk's called Very Visual Machines. It's about computer vision, which is also known as machine vision. Is this my code?
It's fine, yeah.
Okay. So I'm going to start with a quote from cognitive psychologist Steven Pinker that says, "We're visual creatures. Visual things stay put, whereas sounds fade." This directly refers to the fact that we're really good at remembering images compared to other sensory signals, but more generally hints at how central vision is to our perception and our understanding of the world. So if you look at a scene like this, light's flooding in from the sun, and it seems to get everywhere. It's kind of probing the environment for us, if you like. So certain surfaces and materials reflect the light in certain ways, and other surfaces and materials reflect the light in different ways, so that the spectral composition of the light is changing for different materials and surfaces. This gives us our perception of shade and colour, of course. And another kind of useful thing about optics is when light tends to hit surfaces, it tends to sort of reflect in all different directions. Surfaces reflect light in a diffuse way. So the kind of physics is useful to us. People over this side of the room can see the tip of my nose. People over this side of the room can see the tip of my nose. And because it's spreading all around like this, it means when you move your head around, the whole thing's consistent. So what we find is that the structural 3D regularity that we get in the outside world kind of projects to a corresponding 2D regularity on our retinas, and our visual cortex can make a lot of sense of this. It's very rich, it's very comprehensive, and it's extremely useful to us. And it all works. The fantastic thing about it is it all works at a distance. So it's working at a safe distance from this cliff edge, and it's working at a safe distance from the bull that this chap had to pass in a field on the way up the hill. So if you actually look at animals of extremely diverse form, they've all adapted to their environment, and if I asked you what's the one thing that you can see that these animals have in common, it actually might be eyes, especially because we're in this lecture, of course. But, so what this kind of means is, well, eyes are really useful if you want to find your lunch, to find something to eat. But more importantly, they're even more useful if you want to avoid being another animal's lunch. So there's been this kind of evolutionary arms race between predators and prey, which means that there's lots of different kinds of eyes in the animal kingdom. They're very old. In the bottom right here, you've got a trilobite, which is over 500 million years old. So you can see, and there's this bottom left one is a mantis shrimp, which has got 16 different channels of 16 different cones, which split the spectrum into 16 channels. It can see polarized light, and it's got trinocular vision in each eye. So there's some very complex vision systems out there. So kind of the reason I'm talking about this is because if vision is so useful to ourselves and lots of creatures that inhabit our planet, then maybe it's a good idea to give machines vision as well, and then they can do some useful things for us. So this is the general idea of a computer vision system. You have some real-world 3D scene, which is, this is just a stock web image of some wine and cheese. We need to light it with some illumination. It could be the sun, or it could be just a bulb in a room or something. We need a camera, obviously, to capture images. It could be one image or a sequence. And then the important thing for computer vision people is this vision software here, because that's the kind of stuff that we develop, and that's important, to extract some kind of scene description. So we want to encapsulate what's in here somehow, some qualities of what this is in this scene description, so that it's useful for some kind of application software. Okay, so I'm not sure what the application would be for a wine and cheese thing, but maybe it could monitor if we're getting dangerously low on wine, or we've gone critical on cheese, and put some wheels on the thing, it can go and solve that problem for us. So here's, more seriously though, if we're talking about the scene description, I'm giving you a more serious example where it could be about safety in a warehouse. So we've got a vision system looking into this warehouse, and it's extracting objects, or actors in this case, or people from the scene. We've got two men and a woman there. He's standing on a shelf. So the scene description on the right is called a scene graph. So it's got the objects in the rectangles, and it's got some black arrows. They're describing the relationships, and the man standing on the shelf, which actually it's not really a shelf, it's a bunch of pallets, that might be deemed to be dangerous, and so it could give some kind of audible warning to it. So that's one kind of scene description. There's other types of scene description, because this is a little bit image-based. It's just saying that box there has got an image of a person in it. This one over here, for example. But also, you might want to try and explain the image physically. So what I want you to imagine is that you're a photographer, a professional photographer at Wimbledon, and you're at the courtside, and it's your job to capture the pictures. So these pictures, ignore this green haze on this thing here. Pretend this is a real tennis player's head. This is a real sun, the sun's shining outside and bouncing around off everything as it usually does, and you've got a real camera, and you can put all of those things together, of course, and you can take an image, and this happens to be Andre Agassi. And now I want you to reset your mind for a second, and now imagine that those things to the left of the arrow are not real things at all. They're actually models, mathematical models, inside a computer system. So one major sub-problem of computer vision is to take that image as the input to the system and somehow try and reverse the image formation process and be able to extract the parameters of those models. So This is sometimes called inverse rendering, and the reason it's called that is because you could potentially have these models inside a graphics system, for example, and then render them out into something that looks like something is a synthetic image. So here we've got something that could be a photorealistic synthetic image. And one nice thing about this is then we could compare that image with the real image that we had, and if they match up well, then maybe the models that we've extracted are accurate. So that's one, so it kind of closes the loop on it. So you can see that sometimes computer vision is sort of an inverse process, in this context at least, to graphics, and that's in a sense why our research group's called Vision, Graphics and Learning. Vision and graphics feel like they're sometimes inverses of each other, often inverses of each other, and both use machine learning heavily, so that's how that's arisen. We didn't do a full inverse rendering generic pipeline on this, but we did a couple of us did a collaborative project with Imperial, and we tried to fit a 3D morphable model, which is a statistical model of a human head, to these photographs. So these are real photographs on the left. You might notice they all have something in common, which is not very much hair. That's because the model doesn't have very much hair either. So it avoids a complication in that. But what we've done is, from these pictures, you can extract the actual shape of these people's head, and we also extracted the detailed shape of the ear. So the green haze that was there at the start is actually the underlying 3D surface represented by a mesh. Okay, so what I'm going to do now is just give you some idea of where, not really where computer vision, well, it could be where computer vision came from, but it's more really what I want to say is what had to be in place before computer vision could happen. So the first thing I think you have to have is you've got to have images. Otherwise you can't do much, obviously. But image formation, people knew about it for a long time. And it's actually discussed from at least the 5th century BC in Chinese texts. And then it's mentioned over and over again throughout the centuries. Excuse my pronunciation, but Al-Hazan in the 10th century talked about light travelling in straight lines, and you can see this pinhole camera construction at the bottom here, or a camera obscura as it's sometimes named, called. This is literally means dark room. If you've got light travelling in straight lines and you restrict a hole in a wall like this, then you're kind of forcing a one-to-one correspondence between an object in the world and the image and the 2D image of that, which gives you a clear sort of image. And that could happen by accident if there just happens to be a hole in the wall and the image is formed like that. And a lot of famous people like Leonardo and Kepler talked about camera obscura throughout the ages. Once you've got an image, you actually want to store it somewhere. So photography is kind of important in a sense, because you've got to be able to, once you've formed an image, it's got to stay there. Fixing photographs and stopping them being overexposed was a real problem. But the Niepce heliograph is the earliest surviving one. This is a picture of a French estate. It's about 100 kilometres northwest of Geneva, and it's very faded, of course, but it's around that time when this kind of thing was happening. Something that actually surprises me is that it wasn't very long after that when photogrammetry started. What photogrammetry means is that you actually make quantitative measurements from photographs, and it's really quite quickly off the back of having photographs. So the situation here is we have a couple of cameras, and cameras are actually really good at measuring directions. They're not in themselves, in a single view, they're not very good at depth. But if you've got two of them and you move them a distance, then you can measure the angles and make a triangle. It's essentially how stereo vision works, and one of the reasons this good idea having two eyes. And then that allows you to measure the coordinates of this point here, and you can work out the height of the building, for example. So measuring things, photogrammetry is a kind of a sort of founding subject that came before computer vision. What you need to have then is if you've got photographs, you've got to get them inside computers, otherwise you can't do computer vision. And it wasn't until about 1957 that Russell Kirsch scanned his baby son into a computer with a primitive scanner, and then you can start doing computer vision. Remember that digital cameras didn't start to come around until, I think it was the late 1980s. So anyway, everything's in place, you can get images into computers, and it wasn't until the early 60s, and I think the first PhD in computer vision was published in 1963 by Larry Roberts, Machine Perception of Three-Dimensional Solids. And you can see that even back then, they were extracting edges from images in order to understand something about 3D shape. And an interesting thing happened in 1966. Marvin Minsky is a very famous founding father of artificial intelligence. And he gave a group of his students a summer project to do, and his idea was to connect a camera to a computer and get the machine to describe what it sees. And we're still trying to solve that problem almost 60 years later. Of course, it works to a certain extent, but you can't say that that's fully solved. So what I want to do now is say, okay, Marvin Minsky gave his students that thing to do, and we look at this image here, which has got lots of peppers in it, and we could probably count them, see that there's a garlic bulb there. We could say how many different peppers are of different colours, and we think it's easy because it's so natural and effortless for us. We don't seem to be expending any effort to do this. But if you actually look at what goes into the computer, it's just a whole bunch of numbers. So for a tiny patch in an image, it just tells you what the redness, the greenness, and the blueness of that tiny patch is. Okay, so all these, and there's millions of these, of course, because these images are quite high resolution these days. So you've just got millions of numbers going into the front end of a computer vision pipeline. The other thing that happens, as I mentioned before, a camera's very good at telling what directions something's in, but it's not really good at telling you how far away it is from the camera. We call that depth. So is this, and one of the main, there's lots of ambiguities actually in computer vision, but one of the most well-known ones is the depth scale ambiguity. So is this a giant arm that's coming out of the sky that's the same distance as the hill, or is it just somebody who stood much closer to the camera? And it's a sort of, initially it's a compelling illusion, but you soon realise that it's just a trick, and that's because you know how big humans are and you know how big hills are, and because you've got some inbuilt model about things, you can resolve that ambiguity. And it's the same thing with computer vision. We've got to tackle ambiguities all the time when we're, for example, inverting the image formation process, and we often build models, mathematical models, into our processes to handle those ambiguities. And that was taken by my brother, who's kindly come along tonight. So, something about another reason why computer vision is difficult is because you've got to recognise the same object in all kinds of conditions. So here we've got York Minster, but it's in different, the camera when it took the picture, it's in lots of different positions relative to the building. So you get lots of different perspective distortions going on there. You might have a lot of occlusion happening, so the middle one's got a lot of occlusion. And the one on the far right, the lighting is quite bright compared to the others, and it's been raining, so light is reflecting of the surface there, which may confuse things even further. Worse still, if you're trying to recognise somebody's face, you've still got those pose and lighting problems, or variations should I say, but you've also got different facial expressions. A face is a squidgy thing, it's got a jaw that articulates, and so you've got to handle all of those, recognise the person, and you might also want to recognise the facial expression. Worse still, cats are far more flexible than faces, and you may need to be able to recognise cats in all these different positions, and the top left one might be pretty easy to do, but you might have a cat that likes getting too close to the camera, and you've got some kind of perspective effect on the paws. You might even have a cat that hasn't got any fur, but you still want to classify that as a cat. So what's going to happen in that situation? So what I'd like to look at is how there's been a shift in the dominant approach to computer vision over about the last 10 years. So the old style is essentially you put an image into the front of this pipeline, and remember that this is just millions of numbers again, and then you try and reduce this set of numbers to a much smaller set of numbers. It's just a list of numbers, and we call it a feature vector. Okay, so what this is supposed to do is sort of condense the numbers but encapsulate the fact that this is an image of a cat. So if I change this to an image of a dog, I want this list of numbers to change in one or more, in some of the values. If it didn't, then I wouldn't be able to tell the difference between a cat and a dog. So we want our feature extractor program, which is designed by some human, some algorithm, well, a computer vision person, and we want it to have discrimination. We want it to capture information that discriminates between cats and dogs. But we might have this cat really close to the camera, or we might have it far away from the camera, or the lighting might be different. And these are extraneous factors that we really don't want our list of numbers to change, because we don't want them to be influenced by these factors. And this is called invariance, and we want invariance to the factors, all these extraneous factors we're not interested in. But the problem is, if you make something really invariant to those things, it tends to reduce the discrimination power. And it's really quite hard for a particular set of images going in and a particular set of kind of imaging conditions to make this optimal. But anyway, that's what people did. And then this list of numbers would go into a classifier. Now, this is a little bit different because what you're doing here is you have some kind of mathematical model here, but it's got some learnable parameters. And it's a bit technical, the jargon here, but what we used to use quite a lot was something called a support vector machine. But it's a bit like saying, if this vector lies in certain regions of whatever dimensionality that space is, if it's in certain partitions of that, it could be cat, and if it's in other partitions, it could be dog. Or it could be other animals or other objects. And what we tend to do with this kind of thing is we put lots of pictures in the front, and usually these pictures, or in this kind of approach, you would have labels with these pictures, so this would be labelled as a cat. You put some images in to try and train this classifier, and you tell it when it's getting this thing at the end right, and when it's getting it wrong. So when there's some kind of errors in the output, it can change its parameters in this classifier and improve its performance, and it gradually learns how to do it better and better. So that's the dominant approach more than 10 years ago. But what happens now is we have a pipeline that looks a little bit different, and we've got two things to notice about this. It's split into more boxes, but it also, you notice that everything for these boxes has learnable parameters. And that it's actually called something that's called end-to-end learning, And what that really means is you learn the process from, which is a mathematical function, to get from an image to a label. You learn this process in an end-to-end way, which means from the front end where the input is to the back end where the label is. That's learnable. One of the reasons we do this is because when you do this human design thing up here, how do you know that's optimal? And when you learn something, if this is really good, this thing will learn it anyway. But most of the time, this is suboptimal. And when you learn this stuff down here, it ends up being better than this. The only thing I would say about this is, you can often have a lot of parameters in this structure, so you tend to use a lot of data to train it. And that's kind of what's going on these days, is you throw a lot of training data at this structure, you learn a lot of parameters, and the performance of this structure is significantly better than this one, and the performance difference between the two is much higher when you've got a lot of data. And that's, in a sense, this is why people do this now, is because these days you do have access to a lot of data. It's not that this kind of approach suddenly appeared, people have known about it for a while, it's just that everything's come together, we've got data, we've got GPUs, graphical processing units, to train these things, and good algorithms for training. So this has become the dominant approach. And what I'd like to show you in the next slide is kind of how it works. I mean, it's made of deep neural networks. That just means that these boxes are just layers of neural networks. And I'm just showing 3 here. That doesn't mean there's 3 layers. There could be, typically there could be anything from 20 to 100 to 150, something like that. It's just that I want to break it into 3 blocks just to show you in an example application what it looks like for face recognition. So these things, these pictures here, are called activation patterns for a face recognition task. What these patterns actually mean is that when you put a pattern like this is actually like a mini little patch of an image. When you put a pattern in like this, it makes one of the neurons in one of the first layers, or the first layer of this, activate. So it switches on. Okay? So what we find here is you get some bright and dark blobs, but then just a load of bars at various angles. So it's kind of responding when you have edges at various angles. And indeed, this actually corresponds really closely to some experiments some famous people did in the late 50s. Hubel and Wiesel found that cats' early visual processing, their early neurons in their early visual processing responded to signals like this. Okay. What you then do is you look at a layer deeper in the network, and you look at what patterns start to activate those neurons, and they start to look like face parts like this. Okay? And actually these face parts, this might not be the layer immediately after this one, but ultimately these face parts are actually composed of these things. So what's really happening is, if you see this nose thing in the middle, it's actually composed of some vertical bars like this. So what's really happening is when the sort of signals that are, the sort of neurons coming out of this, the outputs coming out of this layer are actually activating neurons in this layer, and it just happens that the arrangement of these patterns is in a particular spatial arrangement in the input, that it makes these patterns and excites neurons deeper in the network. And the same thing goes on here. This time we have whole faces in the input to excite deeper neurons, and then you'll have some classification network at the end. So that's how it's happening. So what's really happening is, you can see this is kind of a hierarchical composition of features, and it's one of the reasons why this kind of approach is quite powerful, very powerful. So I'm going to move on to some current trends in computer vision. I mean, some of these trends have been going on for a while now, but we had a recent talk by Will Smith quite recently, so I'm not going to spend too much time on it. Self-supervised learning. So one of the problems with training deep neural networks is that they require a lot of data because they have a lot of parameters to learn. And that means you need, in a, let's say, cats versus dogs classification, you need loads of pictures of cats with the label cat, loads of pictures of dogs with the label dog, you need millions of them. And who's going to label all those? It's a bottleneck that prevents us scaling up to bigger and bigger data. So it's much better to try and get the machine to learn itself for a while on something called a proxy task or a pretext task. This is a task that, in a sense, you're not bothered about the result of it. It's just like learn some task that helps you do this important task over here. So in terms of the cat, suppose you took a cat image and you broke it into pieces like a set of squares, a bit like a jigsaw puzzle for children. What you do then is you get the computer to sort of scramble these and forget for a moment where the parts came from. It will use them later, but let's say it forgets for a moment where the parts came from. What we then ask the computer to do is to reassemble the jigsaw and see if it can do it in the correct order or as close as it can. And then, since it knows what the correct order is, because it broke it up itself, it can actually rate itself on that and gradually improve its performance. So in order to do that, to know that eyes are above a nose, which is above a mouth on a cat's face, it has to extract features and understand the spatial relationship of those, and therefore it learns important visual concepts about what it means to be a picture of a cat, and it can learn from that, and then it needs far less supervisory information in order to classify cats versus dogs, for example. There's other kind of proxy tasks you can do, like deleting parts of the image and asking it to fill it in, or rotating an image and asking it to predict the rotation that it itself made, and so on and so forth. So, but you've got to be a bit careful about designing these proxy tasks, because if the machine finds cheap tricks to solve the problem, then they might not be that useful for solving the cat recognition problem. So you've got to design those pretext tasks with some care. The other thing that's happening and happened a couple of years ago was new neural net architectures. There's a long history of a particular type of neural net called a convolutional neural net that works really well in vision because it looks at local spatial patterns and builds up on that, just like I showed you in the human face recognition thing, how you have compositional feature construction through the network. That works really well, but the thing about it is that if you think about an image going in and think about a patch of pixels, there's no real connection between that patch of pixels and a patch of pixels a large distance away in the image. You can't learn if there's any correlation between them if you're just looking at local patches. So a new architecture came in called a transformer, which was very, very successful in natural language processing, and it's a thing that's in ChatGPT, which you'll have heard of in the news, and that's actually, last couple of years, that's being extremely successful for computer vision problems. And probably something will come after transformers and replace them, but who knows. Another thing that's happening is multimodal systems. Computer vision is being paired with things like natural language processing because it feels like a much more natural way to interact with information in an image. If you cast your mind back to when I talked about the warehouse application, which was about a camera looking into the warehouse and about the safety of that, what if that scene graph wasn't something you cared about too much? And the system wasn't really telling you the information that you wanted to know. Wouldn't it be better to just be able to ask that image some questions? So you have this concept of visual question answering, where you could say what's in the image and what's happening, and just keep questioning until you get the information you want. And there's those sorts of systems around. There's a famous one that deals with this picture where the system might say, oh, I can see that a famous person, Obama, is in the image, and then you might ask it how many people are in the image, and it tries to count them. And it does this particular, I think it's a flamingo system, actually does that quite well and manages to avoid overcounting even when the mirrors are there. So that kind of thing is working pretty well in some cases. And I think because we use natural language and we want to think about image understanding, then it's kind of on our wavelength, and it matches up with our own concepts about images if we use these things. Another big thing, again, on the news is generative models, and that relates to creative industries. So there's been a bit of a hoo-ha about AIs creating alternative artworks, some very famous works. This is an example. Vermeer's Girl with a Pearl Earring, and then it can create something that's of that style but different. Maybe it's the difference between home baking and a shop bought one, I'm not sure, but that's happening. And if you put those last two bullet points together, multimodal systems and generative models, there's a lot of stuff out there now where you can type text prompts and they generate images for you. So for example, this one, I typed in woolly robot sheep with camera eye, and that's what I got. Okay, so I think that's the end of the first part of the talk. What I want to do for the second part of the talk was just take you through some of the projects I've done over my career, and I actually didn't immediately get into computer vision, as Paul mentioned. I actually started in Durham and looking at robotics. So I guess you've all heard of Dolly the sheep, but have you heard of Molly the trolley, which was my PhD project? Back then, you couldn't buy. It was so long ago. It was in black and white as well. You couldn't actually buy robots, and if you could, they were really expensive. So I built this for my PhD project, and so while my PhD students are looking on the web for tips on how to train deep neural networks and tune hyperparameters, I was looking in a thick book like the Yellow Pages, to find a couple of car batteries and a welding torch. So it's a bit different. And you can see there's an old floppy disk on there, a couple of big motors. You could actually stand on this thing and it could carry you around, which was quite fun. But the point of this was to try and work out where the robot was using ultrasonic rangefinders, which are these transducers you see here. And then once I located the robot in the lab, I designed the steering control systems for it to follow some pre-planned paths. And then I did my postdoc in Oxford, and what I did there is I got into optical sensor design and built this thing, which is a scanning laser rangefinder. So I'll use my pointer to say what it does. So it gets a laser like this, and it sort of scans it really quickly backwards and forwards like this. And then it has a camera looking from a different angle. Now, with binocular vision, you can work out what depth is because you're looking at two different angles and you make a triangle and you get the depth. But if you replace one of those cameras with just a laser, you've got the direction from the laser and you look from a different angle and you get the depth that way. But one of the problems is if you scan something like this, like that, you're changing, and you keep the camera fixed, you're changing the geometry of all of that. So what the trick that this thing does, and I have to say this wasn't my idea, I used a variation of synchronized scanning from the National Research Centre in Canada, where what they did, and I did this as well, was you use the front and the back of the same mirror to scan the laser and the camera in synchronism with each other. So they go like this, scanning in synchronism with each other. So probably I'll try and get this to work. So you can see the oscillating mirror like this. This is like 90s, so it's quite a long time ago. You can see how old the monitors are, and then there's a box in there, and it's just scanning away like that. So it's just getting depth in the plane, really. That's all it's doing. And then what I did later was, it's got a 40-degree field of view, so I put it on like a rotating head, so when things come nearer it, it can turn its head and attend to them. And then what I did is I put it on a bought robot, so you can see that I've put an obstacle there, and I've also got an obstacle avoidance algorithm. It's a bit heuristic, but it's basically trying to fixate on the obstacle that's cleverly being put in the scanning plane of the sensor, so that it has got a bit of weakness. If that was too low, it wouldn't see it. And then it can use its head to sort of fixate and kind of build a little local map of its environment and essentially navigate through. And obviously that worked first time, which was really surprising. Okay, I carried on, and when I first came to York, this is actually the old building that we're in. Keith Mander was the head of department at that time, and kindly gave me some money to buy a robot, and I bought this little thing, because it's much easier than making one. And what I wanted to do was to track features to actually find out where the drivable region was. So this is it sort of moving along the top corridor. That line's supposed to be the horizon line. It's not very stable, but it gives quite a pleasing outline of where it can drive. It's even got the cutout of the door here that's this bit in here. So so what I'm trying to do is I'm getting into vision, because I was feeling that for all the reasons I said at the start of the lecture, vision being comprehensive information source, parallels with biological vision, and also the challenge of getting the information out of that ambiguous and high-dimensional signal was the reasons that I wanted to do this. So I'm going to go to some applications. I've talked about why vision is challenging, and I want to also say why it's useful, and I want to use some of the projects I've done as examples of that. So security obviously is a bit controversial, I know, privacy and all that kind of thing, but I've worked in face recognition, but the kind of work I wanted to do, it was straight after, I got into this straight after 9/11, it was a big thing, security. We did some 3D face recognition, so using data coming off 3D cameras, trying to recognise faces in that way, and also some work in trying to localise the face before we cut out the part of the 3D scan, which is shown here, and sending it to a recognition engine. There's transport, we've done some work in that. This is the campus. Again, it's not very high resolution, but we segmented some vehicles, segmented the shadows of vehicles, then cut the vehicle out and sent it to classifiers to classify it was a car, van, lorry, and then the purpose of that was to check there was no plate cloning, so the vehicle type matches up with the number plate that it's supposed to have. I'm going to talk this in a bit more detail, but this is my clinical collaborator, Christian Duncan's here, and he's a craniofacial plastic surgeon working over at Alderhay, and what we wanted to do was build some statistical models of the human head in order to have some kind of tool to assess the outcome of surgery when treating very young patients, babies and infants, with a condition called craniosynostosis. This condition is when the bones that are in the skull, in the cranium, they have sutures, which are flexible joints, if you like, that allow the brain to grow. But if these fuse too early, then you have all kinds of problems. There can be there can be pressure inside the cranial vault. It can be, it's thought not to be good for the development of the brain and so on. And also, you want to improve the shape of that, of the cranium. So we've done some work on that. I've got more slides on that one, so I'll come back to that one. We've done some work in sports, essentially classifying different motions, running, jogging, walking, boxing. It's a bit like, the way this worked is, if you imagine on a bonfire night and you've got a sparkler and you do this with arms, you have like a persistence of vision, and we built a sort of feature detector that did that kind of thing and then classified it. I've worked in HCI. We built this idea we called it display registration, but it's being taken up in the HCI community, and it's called touch projection now. So the idea is you put a mobile phone up to a display, and there's some kind of wireless link between them, like Bluetooth, and you capture the image of the display with your smartphone, and then you send that image to the PC, and what you ask it to do is to register the two images, which is a relatively straightforward registration in computer vision. And that means that when you actually touch your smartphone, you can send that touch also over Bluetooth to the PC, and it knows where you've touched on the PC screen. So you can actually use it to interact, for example, with a remote display. It could be really high up in an airport, or it could be the other side of some glass in an estate agent. So that's something we did, and yeah, a while back. Manufacturing is a big thing. I haven't really published much in this, but I've got a project going on at the moment using cameras with Shibao and Pengsheng it is, to guide a mobile, a manipulator. I've worked in retail. This is an interesting application of computer vision. Track people, track what they put in their baskets, and then they don't have to scan items out when you leave the shop, for example. You just pay for it. And then farming, they say don't count your chickens. Now we don't have to, because you can actually get computer vision to do it, and you can monitor what the different chickens are doing, for example. If I was selling this one, I'd give it a freebie, and that would be a fox detector, just in the marketing to sell it on. Okay. Just scratching the surface with this application for agriculture. Right. I'll move on quickly. This is the project I did with Christian, who's in the audience. Craniofacial shape modelling. Again, it's for this craniosynostosis application. We've got a patient in this cage, and there's 5 3D sensors which can extract the shape and also the texture. And so they're kind of, sorry Christian about this, it's your head, rotating. So you can't do this with normal photographs, of course. So we've got the full shape of the head, and we've got that kind of data. And the problem with that data is that it's coming off the sensor in a random order. The surface points, they're not ordered particularly. Also, Christian's head might have a couple of 100,000 points on it, but if we scanned a baby's head, it might have far less. It might have far fewer points. Okay? So we've got to normalize this somehow. So what we do is we take a template which has got a fixed number of points and a fixed structure, and we know that, for example, the 1000th point is always the nose tip. Then we can regularize everything, we can normalize everything. So this morphs to the subject's face, and we repeat this process for over 1,000 people. I think we did it for 1,200, and we end up being able then to find an average head shape, and also the major modes of variation of that head shape. Okay, so essentially we see things like this. The major mode of variation is kind of size, and then various other modes. Maybe if I stop it on 4, if you look at mode 4 and I'll just slide it, it sort of has bigger noses which look a bit male, but as you go through that mode, you have smaller noses that look maybe a little more female. And when we're moving through these modes like this, when we move through a mode, we're only changing a single number in the model, a single parameter in the model. Okay, it's the first mode is the mode that expresses most variation in the training data set. The second mode is the number, when you vary it, that expresses the second most variation in the training data set, and so on. So the one on the side, we also built a model of texture. You can see the caps changing from blue to white because some of the subjects had blue caps on, some had white. And you can actually build statistical models of different age demographics. So here we're doing it for under 15 and here over 50. The one on the left here is essentially the mean shape. That's the mean shape of that group. And then you can see the primary mode of variation, and the secondary one, the tertiary one, and so on. So you might say, okay, that's fine, but how do you use it for craniosynostosis? So if you look at this particular case study, you've got a particular type of operation which is called total calvarial reconstruction, is that right? And what you're really doing is you're looking at, this is the patient before the operation, this is the morph template, this is the patient after the operation, this is the morph template. Okay, you can see that the cranial shape is much better here, but that's a qualitative thing to say that's better than this one, but we can actually measure the change with our model, because our model, if you think of this blue point, which has the parameters set at 0, actually means that it's not this middle one is the mean shape. This is the pre-operation shape, and this is the post-operation shape, and this blue ellipse here is the 2 standard deviation ellipse of all these little dots, which are the training people in the Headspace dataset that trained this model. So we can see that before the operation, the patient has a head shape that's more than 3 standard deviations, or about 3 standard deviations from the mean, and this one's maybe just over 1 standard deviation from the mean. So quantitatively, it's improved as well. And we did this for 2 different operations and about 17 different patients. And you can see Christian's doing a great job, because all the pre-ops seem to be outside the 2 standard deviation ellipse, while all the post-ops seem to be inside the 2 standard deviation ellipse. And if you plot the pre versus the post number of standard deviations from the mean, which is Mahalanobis distance, you can see that it's just over 3 before the operation, and after the operation it's just over 1, which is significantly better. And this, so our models were used for this particular application, and we've got an ongoing collaboration. But more generally, our data set, which is shown here in different poses and lighting conditions, and our models have been distributed to over 150 research groups internationally. So that's had good impact. We've also built models of the ear, so you can see the average ear and the major modes of variation of an ear shape. And this has been distributed to over 30 research groups internationally. And all the models we've done together, I think it's over 200 research groups internationally. So we've had good impact. I haven't counted the double counts, as in, there might be more than one person from a research group doing it, if you see what I mean. So, anyway. So I wanted to show just a use of the ear model, which was done with House Son, who's recently graduated with his PhD. So this is taking celebrities, and actually he trained a neural network to extract pose and ear model parameters to fit a 3D model to actual photographs of celebrities, so we actually, from these photographs, can work out what the celebrities' ear shapes are. This might be useful for designing earbuds for them, for example, for personal stereo or something like this. I've briefly mentioned, I'm coming towards the end now, but I just wanted to say what I was doing. I'm not going to read too much out. But this is the blue are my current PhD students, and the green are who I'm supervising things with. So I've got a couple of PhDs still working on intrinsics, on morphal models. This one at the bottom is an interesting thing we've done recently. It's a text to 3D face with Will Rowan is the PhD student. So we put a text clip in, 20-year-old woman looking at the sky with surprise at UFO overhead, and it generates the 3D shape of that. This text is generated from DALL-E, and then it's stitched on top to give this kind of structure straight from text. I've got working with Tejas and Josh on sort of safe transport. Tejas is doing autonomous driving, and Josh is doing vision-based safety for urban railway. And as I mentioned, I'm doing some vision-based robotic pick and place. So the takeaway messages of the talk are visual machines can usefully exploit the same rich information that visual creatures use. A lot of computer vision technology already works well enough. What I mean by that is it can automate tasks for us now and be really quite reliable at it. But other things need more work, and I would say especially safety critical applications, because when you've got something like this, a self-driving car, it can't, you need to be sure, you need to be careful about this. You want people to have confidence in it, you have to have transparency in the way it works, and so on. This actually fits in with our ethos in the department of safe, ethical and secure computer vision systems. We want these things to be safe, we want them to be secure because they have to be resilient to attack. If you change a few pixels in an image, you don't want this whole thing on the right to break down and give you different answers. I think there's going to be much more to come. I'm not sure what it is because there's so much happening so quickly now, but I think there'll be new concepts, new technologies and applications that we've not even thought of yet. So for us in the field, it's technically and creatively challenging. I think the best thing is to see our ideas, maths and code come to life in systems that really work and serve the greater good. So I want to thank everybody that's worked with me. Sorry about that. Thanks to all my co-authors, and I've listed some headings here. I haven't put the names down, and there's a few papers on the right. And thank my family for supporting me in all the nice holidays. And thanks for listening. Any questions? Hang on, could you wait for the mic? And then
Sorry.
There's a mic coming.
Thank you. I'd just like to say that human beings generally have incredible background knowledge which you're not even aware of, and that when you showed the image with the guy on the weighing machine and while we're putting his foot on there, most people would instantly recognise the humour. A machine doesn't know about humour. It has no background understanding other than what you've programmed and the data you fed in. So incredibly limited, yeah?
Yeah, I agree with you. I mean, if you actually go and look at the picture that you're talking about, there's some dialogue online, and I think the last thing that it actually says is, do you think this funny? And the machine says, I think so, but it doesn't sound very sure. But I think all those things you say are true. I think that the point that you made is interesting in that we use a lot of models in our mind to disambiguate and understand all the signals coming in. It's almost like we're sort of reaching out with our predictions in order to actually shape all the perceptions, because it's just far too ambiguous anyway. Yeah. And I think that's what's happening with machines, in a sense, that we have to build models in to interpret ambiguous signals. Yeah. But I think the built-in knowledge is far smaller in machines, and therefore it's far more brittle, and you can see the cracks in it quite quickly. I think you're right.
Yeah. Thank you very much.
So you might be able to answer a question, because I was in a meeting on Monday, we were talking about visual classifiers as part of our research. So we were talking about the situation, and I'm wondering how possible it is, where a classifier, a machine learning algorithm, says, I believe it is a cat, not a dog, the image I'm looking at. But if you run this other classifier, I'd be more certain. How feasible is that in practice?
Why don't you run the first one in the first place? Exactly. So, you run a classifier and it's not sure, and then try and run another one. Is that what you're saying?
Yeah, basically.
So is the first one faster and cheaper or something?
Yeah, basically that's the context we're working.
Yeah, I think you can do that. Yeah. So you could do something. I think you could do something like that where. If you've got a small network that performance is less, but it can go really quickly, and then if you're sure, if the small network is sure, then that's fine. But if it ends up, normally these things do things probabilistically anyway, so that if the probability says it's 0.5 for a cat, then it would be a good idea to run the bigger network and then see how that probability shifts. It might actually stay the same if it's a Cornish Rex, for example.
I think the context is for the bigger classifier, the more complex algorithm, there may be a choice of which ones to choose at that stage, and based on the particular image, you would choose which direction to go next.
Okay, so... Okay.
We'll talk about that later.
Yeah, all right.
Hi Nick, thank you very much for a really interesting talk. One of the things, you talk about the cross-modal work, so language helping with vision, but actually the way we learn an awful lot about the world is through interacting with it. In fact, getting your hands to work is one of the most difficult things children have to learn as well. What's the opportunity, what do you think is the opportunity there for interaction to inform these models?
Yeah, so I guess having systems that have to interact with the world, so getting feedback from as you say, I guess that kind of thing goes maybe in the robotics world a little bit, but I guess you could do it in simulation as well. We're very good at simulating environments now, so having agents inside some kind of simulation that are using vision and language, but trying to solve problems, and actually, given that you're simulating everything, you actually have access to what the ground truth is, and therefore that might be quite a fruitful stream to do everything in simulation, but in a kind of much more interactive way that you're talking about, actually interacting with the environment rather than, being given labels isn't really the way to do it. It's more solving problems and understanding the connections between these different encodings of languages and images and connecting them in some way.
Thanks, Nick. That was great. My question is about this relationship between vision and graphics, which luckily for your group you handle both. So how close are we to creating systems where others, like humans or others, can't distinguish between the real and the generated, if you like? So you can't trace it back to anything where you say this is real or fake.
Well, I'm probably not the best person to ask, as people know more graphics than me, but I think photorealism is getting really good now. And it is linked to machine learning, of course, because there's a lot of generative deep networks that actually essentially try and essentially generate stuff that isn't distinguishable. That's the whole way that something like a GAN or a generative adversarial network works. It generates images, and then it also tries to learn how to distinguish between a real and a fake image. And it's so good at doing that kind of stuff, if you have a very deep network, that you end up with synthesizing images that the network is struggling to tell whether they're real or fake. So I think it's getting to that point, and obviously it's kind of a problem, because you start thinking, I don't know if this image is real or fake, and it's weird what's happening, because people are actually using the fact that saying that real images are fake when they're in fact real images, to there's kind of both sides of that coin going on at the same time. So I think they are pretty good, yeah.
Any more questions? Yeah.
Hi, I'm just wondering, you showed us your work from your PhD, and in a way we're still doing some of these very similar things. And which time period did you find more exciting to work in? Was it back then or today?
Oh, that's a tough one. I find both exciting, but they're different. I think the thing about computer vision back then, I'm not going all the way back to when I did my PhD, but the way you used to do things was you'd think of an algorithm and code it up quite quickly, and you could quite quickly tell, how well it was going to work. And we did sort of quite a lot of maths in sort of linear algebra, and thought about manifolds and all this kind of thing, and built and designing features, like I said, that were discriminative and invariant. And now we train big networks, and it's great. I think it's great that training the big networks gives fantastic performance, but you're sort of thinking, sometimes it feels like it's a bit of an engineering discipline, that how good are you at selecting architectures, and how good are you at training networks, and it kind of takes a long time as well, which is sometimes frustrating. So I kind of feel sorry for some of our PhD students who have to train networks over days and days and days. That's a little bit frustrating, and so I think they've both got their qualities. I'm not going to pick one, and I've enjoyed both.
So, thank you very much. I think it's sort of time to finish the question, to let Nick off the hook. But just to say thank you again for a really entertaining talk, and I'm sure you'll join me in thanking you again. So thank you very much.